Okay, so let's get started. The title of my talk today, NoSQL Core Concepts. My name is Guy. I'm head of training at ScyllaDB. Few words about myself. I'm in charge of learning and training at ScyllaDB. I've been with the company for about 6 years, which is quite a lot. My background is as a software engineer, and I am based in Israel, which is where I'm taking this call from right now. And about a month ago, I did a talk. It was titled Advanced Data Modeling to the same group, to Big Data Demystified. And I got some feedback that people were interested in more basic concepts, like getting started, intro to NoSQL, some stuff like that. So that's where the idea for this talk came from. So based on your feedback, I don't know if you were on that call, but based on your colleagues and your feedback. And today we have about 1 hour, a bit less, because I want to leave some time for questions. And I plan to talk about the following topics. So I'll start with an introduction to NoSQL and to ScyllaDB specifically. And then before I get on to some concepts, architecture, and so on, I just want to show you a hands-on lab, just how quick and easy it is to get up and running with a database, to start a cluster, and to perform some queries. So we'll do the lab, and then I'll talk about some theory, basic concepts, architecture, what happens when we read and write data to the cluster, to a database. And then if we have time, I'll touch a bit on some basic data modeling concepts, but data modeling is a big topic. I can talk just about that for an hour or maybe for an entire course. And then if we have time, we'll just show you another lab. And as a side note, all the slides and the labs that you're seeing are going to be shared with you, okay? So you don't have to worry about, I don't know, making photos of the slides or writing down links. I'll send you an email with the slides and with the links, and you can take the labs and run them on your own. So you can do that through a resource that's called Scylla University. And you can see it right here on the left-hand side, university.scylladb.com. And that's the Learning and Training Resource Center. It's completely free. If you want to get started, you just create a user and you start learning. It's self-paced, so we have quite a lot of material. Lessons covering different topics, data modeling, drivers, you name it, NoSQL related, it's there. So I highly recommend that if you want to dig deeper into different topics that I'm mentioning, but because of the time and the scope, I can't really cover everything. So have a look at Scylla University. The second resource I want to mention is documentation. So that's docs.scylladb.com. And there you have in-depth manuals, how to do different procedures. And yeah, if you want to check out specifications or arguments for a specific command, stuff of that sort, you can look at the documentation. So I see quite a few more people joined. So if everyone can just, most of you are with your videos turned off, just so I know that I'm not talking to myself. If you can just say your name in the chat window and maybe where you're from and what you're drinking right now. You can say hi in the chat window. So we see there are more people here. So for those that missed my introduction, my name is Guy. I'm based in Tel Aviv, Israel. And I was just drinking some kombucha, actually, with soda, but now it's finished. Okay, so as you say hello in the chat window, let me move forward. Okay, so let me start with an introduction to NoSQL and also to ScyllaDB. So I'll start by saying that ScyllaDB is a distributed database, and that means that just as it sounds, it runs on multiple computers. It's one piece of software that runs together on multiple computers, on multiple servers that are possibly located in different locations, different data centers, different countries, and they all work together. What we see here is also called the CAP theorem. And the CAP theorem states that for distributed databases, we have three attributes that we want to achieve or strive for. However, we need to choose two. So like in many other things in life, we have a trade-off. We can't have it all. So we have to choose two out of those three attributes. And these attributes are consistency, availability, and partition tolerance. Now, maybe in a few words, what each one means. So availability means that no matter what happens, our database will still be serving requests, okay? It will always be up and running. It will always be available. That's availability. Partition tolerance means that because we're talking about a distributed system, it means that even if there's a partition, like a network failure, or a split between the different nodes or servers in our software, then the system will still know how to react to that and will still be able to serve requests. And finally, consistency means that for every, well, there are different ways to define consistency, but one definition that's simple and that I like to use is that for every read that we perform, for every read query, we're always going to get the latest write. Okay, so that's one way to define consistency. Now, as I mentioned, we have to choose two out of the three. And here I wrote, to be honest, a few random databases. I could have written many other ones as well. If you look at DB rankings, they have a list of, I don't know, maybe 200 databases. And yeah, it's a large world of different offerings, different types of databases that achieve different things. So just a number of names that I put here on this triangle. So we can see MySQL and Vertica have a preference of consistency and availability over partition tolerance, while databases such as Cockroach Labs, Apache HBase, MongoDB, as well as many others that I didn't mention, give a preference for consistency over availability. Okay, and the database that I will focus on today, here you can see ScyllaDB, Apache Cassandra, and Amazon DynamoDB, as well as many others. They give a preference for availability over consistency. Okay, and what does that mean? It doesn't mean that the data is not consistent. It means that the data is eventually consistent, and I'll talk a bit more about that and how we can configure that in just a bit. But they give a preference for availability over consistency, and that means that these databases have a very high availability. Okay, so they can work even if there are some disasters, there's an earthquake, a fire, a computer goes down because of some hardware malfunction or any other reason you can think of. So that's one way to think about it. And I didn't really say it, but this talk is live. It's happening right now. It's not pre-recorded or anything. So feel free to, I'm looking, I have the chat window open on another window. Feel free to tell me if I'm going too fast, I'm going too slow, if it's boring for you. If you have any questions, write it in the chat window and I will try to look from time to time, and if there's enough time, I will answer. And I will also try to leave a few minutes towards the end for Q&A. Okay, an advanced version of the CAP theorem is called B.SC. I don't even know how to pronounce that, but that one states that it talks about the trade-off between latency and consistency. So it says that even if there is no partition tolerance, if we have a higher consistency, we're going to have a lower latency. And that goes to talk more about performance, which I'll also talk about in just a bit. Okay, another way to look at NoSQL databases is according to the data model. And again, some random databases that I wrote here, I could have used different names. So ordering them from the least complex to the most complex, we have different data models, the easiest being key value. Examples are Aerospike and Redis. Key value, as simple as it sounds, we have a key and we have a value. So no need for advanced data modeling or a schema or anything complicated. It's very simple. And that has its pros and cons. And with databases in general, and specifically NoSQL databases, I wouldn't say there's like a good or a bad database. It really depends on your use case and on using the right tool for your problem. Okay, so it's really important to look at the problem that you have, at the type of application and the requirements from that application, and use a database that would be suitable for your specific needs. Great, so I talked about key value. Next, in terms of complexity of the data model, is a document store. Think about MongoDB or Couchbase, some well-known examples. And with document store, data is stored in a pre-formatted document type. Think about XML or JSON. And that has its pros and cons as well. Next, in terms of complexity, we have wide column store databases, which I'm not so crazy about that name, but that's just how it's called. And here you can think about data as tables. So we have rows and we have columns. And examples here are ScyllaDB, the company that I work for, Apache Cassandra, Amazon DynamoDB, and some others. And finally, we have the most complex data model, which is graph databases. And here, two well-known ones are Janus Graph and Neo4j. There are some others. And with graph databases, data is modeled as edges and vertices, okay? So these are different examples. My focus in this talk will be on wide column store databases. However, many of the things that I will talk about will be relevant for other types of databases as well. And as an example, I will be using ScyllaDB as the database that I will talk about. Probably all of the concepts that I'm going to talk about when I talk about architecture, data modeling, and other concepts are relevant for Apache Cassandra, which is a very well-known, highly used database, as well as for Amazon DynamoDB. And maybe I'll mention it later as well, but ScyllaDB is actually API compatible with those two databases. So that means that if you're running an application on Apache Cassandra or Amazon DynamoDB, you can switch the underlying database to ScyllaDB and use your application pretty much as it is. Great, so maybe a few words about ScyllaDB. We have some companies that are our customers that you probably heard about. You can look at the logos, I don't need to read them. Some of the attributes of ScyllaDB. So I'll start with the last point maybe, which I just mentioned, and ScyllaDB is a drop-in replacement for Cassandra and for Amazon DynamoDB. It was developed, started its development about 10 years ago. And the idea was that Apache Cassandra had some performance problems. It's written with Java, and ScyllaDB was written from scratch with C++. And not just that, but also it had many other improvements. Yeah, I can talk more about that, but yeah, no, it's not that interesting. If you have questions, you can ask me about the specific architecture. Things that were we had in mind when we built the database was low maintenance, so the system can auto-tune itself, high performance. So if we compare it to Cassandra or DynamoDB or others, we get up to ×10 the performance. So it's really fast. It's very highly scalable. And that's important. That means that I mentioned that it's a distributed database. So it works on multiple servers. And it's possible to add or remove servers as the system is running. So just for example, say it's you're running maybe an online e-commerce website and Black Friday is coming up. you know that you're going to need to serve more requests, you're going to get more traffic, you can simply add nodes a few days in advance. The system will scale horizontally, and maybe after Black Friday, traffic goes down, you can remove those nodes, okay? So again, there we also have a trade-off between just the cost of the hardware, right? Because we need to pay something for the hardware. And the last one is high availability. So the system remains up and running. And that's a big point in the design decision. And I will also touch on that when I talk about the different concepts and the architecture and the data modeling. I also didn't mention it, but ScyllaDB is open source. Okay, so open source software, community-based. You can look at the code, you can compile it, run it yourself. We have some community members that are contributing. If you want a feature developed, you can develop it yourself, send a pull request. So that's one option. In terms of ecosystem compatibility, I won't really get into that, but everything that works with Apache Cassandra, which is a big ecosystem, works with ScyllaDB. Drivers in the most common languages and different integrations. Yeah, you can just ask me if you are interested in a specific integration or Google it. We have a lot of information online. So I mentioned performance. We have different benchmarks on our website. I don't want to go into the details, but maybe just let's look at one example comparing to Apache Cassandra. So we had one of our customers replacing 40 Cassandra nodes, and the node is basically a machine, a server running the database software. So we had 40 Cassandra nodes replaced with 4 Scylla nodes. It was 2.5 times cheaper and had 11 times better latency. So again, all they had to do was replace the database. The application stayed as it was. And if you're thinking about changing to a different database, you can look at these benchmarks with much more details. It will probably bore you on our website. And here I put a link to the example by one of my colleagues, and you can see how easy it is with just a few clicks of the button to start your own cluster that runs 1 million operations per second on a single machine. Okay, so you can see an example. You can try it out for yourself. Don't take my word for it. And that's a really cool example. Okay, so I mentioned open source. You can look at the GitHub code repository, and there you get the latest features, and you can hack around the code if that's your thing. The next option is ScyllaDB Enterprise, which is our production-ready release. And with that, you get a few more features. But maybe the main thing here is that you get our support. So if you're running a mission-critical application in production, you can use the enterprise version, and then you get 24/7 support. And last but not least is ScyllaDB Cloud, and that's our database as a service offering. For all the examples that I'm going to show you today, the hands-on labs, you can run them on ScyllaDB Cloud. And with just a few clicks of the button, you can start a cluster. It's very straightforward. You can do it with a free trial. And yeah, we see more and more, a large majority of our customers are now choosing to use ScyllaDB Cloud because they're saying we don't really want to administer a database. That's not our core business. We want to focus on building whatever application they're building. And then with ScyllaDB Cloud, we take care of the administration, security, backups and repairs. And of course, you get support, so you don't have to worry about running the database. Okay, great. So I've talked for quite a bit. Let's see a lab to see how it looks in action, a hands-on lab. So I'm going to be using a platform called Instruct, and this platform, a platform called Killer Coda. So this platform allows us to run examples in our browser. Okay, so it doesn't require any prerequisites. All you have to do is have a browser and an internet connection. And before I started talking, I just clicked on this command. And this command uses Docker to run a single instance of Scylla with a specific version. So what it did, it just downloaded some files and started the cluster. You'll have to believe me, I didn't want to waste those few minutes that it takes to do that. Now that the cluster is running, I clicked on this command. And what this does is it performs a command, called node_tool_status. And that shows me what's the status of my cluster. And my cluster has one node with a status of UN up and running. And basically that means that it's ready to serve requests. And I know that I'm saying things now that I didn't really explain, but I'm going to explain them in just a bit. I just want to show you how easy it is to start. I connect to my cluster with a CQL shell. That's a command line interface that I can perform queries with. Once I'm connected to my cluster, I create a key space. Okay. Using that key space, I create a table. This table has 3 columns, a user ID, first name, and last name. And once that table is created, I can insert some rows into my table. So I insert 2 rows. If you're coming from a relational database background, then this probably looks very familiar to you. It's not anything unique. And I select these users that I just entered. And once I do that, if everything goes according to plan, then I'm supposed to see my data. So classic for a demo. It's not working. Let's give it another few seconds. There it is. Okay. So I created a key space. I created a table. I inserted 2 rows, and not surprisingly, when I read those rows, I can see that I get them from the database. So that's how easy it is with just a few clicks to get up and running. And of course, you can do much more interesting things. And I hope we have time for me to show that to you in the next lab. So I will share the link to this lab as well as to the slides and other material in the email that I send you. Okay. Let me start the next lab. So we're going to save some time later on. So the next lab, I hope I have enough time to show you, is it deals with high availability. And it's a more interesting, more complex lab. I definitely won't have time to show you everything, but I hope to just show you the beginning of it. So let me just start the cluster so we save time later on. Okay, while that's happening, let's go back to the slides. Great. So we are here with the quick wins, and moving forward, let's talk about some basic concepts and architecture. So I already said that, but let me say it again. The things that I talk about, the concepts and the data modeling, are relevant for ScyllaDB, which is being used as an example. They're also relevant for Apache Cassandra and DynamoDB, and also for other databases, okay? So I kept saying a node. What is actually a node? So a node is basically the database software, ScyllaDB in this case, running on a computer, on a server. That's a node. And a node in ScyllaDB consists of different shards. Shards are basically threads or hyperthreads or virtual CPUs, but I won't get into that. And each node in ScyllaDB contains a portion of the database content. Okay, and that's important. So in ScyllaDB, data is replicated, and that means that multiple copies of each data are held on different nodes. Okay, and that goes together with high availability. So even if one node becomes unavailable, we can still serve requests because we have multiple copies. In ScyllaDB, as well as Apache Cassandra, of course, all nodes are created equal, so they all work together in a distributed fashion to serve requests. We don't have the notion of follower leader, master slave, or whatever other names you want to call it. All nodes are created equal. And again, that goes together with high availability. We don't have single point of failure. So I mentioned that nodes work together in something called a cluster to serve requests. This is how we conceptualize it. And in this example, we see a 5-node cluster. These 5 nodes are working together to serve requests. And in production, so in the example that I just showed you, the quick wins one, we had just a single node. That is only relevant for the lab. In production, a cluster should have at least 3 nodes. And the number of nodes is completely up to you as the user and to your application and to your requirements. So in production, a cluster can be between 3 nodes, and it can go all the way up to hundreds of nodes working together as a single cluster. Okay, so it really depends on your performance requirements, on your availability requirements, on geographical location, maybe on some compliance reasons. Okay, so there are many, many attributes that you want to take into consideration when you determine the sizing of your cluster, but that's another big topic. Okay, so I mentioned data is replicated. I see there's a question about if I can share the web link. So sure, I will share the slides and the links to the labs, and all the links that you see here will be shared. I will send them by an email to everybody that is here, probably tomorrow. Okay, so don't worry about copying things or writing things down. I'll share that with you. Okay, so data replication. I mentioned data is replicated across different nodes. For each piece of data, we copy it to multiple nodes, and the number of nodes that where data is replicated is defined by a setting called the replication factor. Okay, replication factor, also abbreviated as RF, and that is something that you as the user determine according to your needs. So if, like in this example, I set for the key space. Okay, so a key space, I didn't mention it. A key space is basically a container for tables in the database. And the key space has different settings. Maybe the most important one is the replication factor. And here in this example, I create a key space, calling it my key space, and it has a replication factor of 3. What this means is that all the tables within this key space are going to inherit this setting of replication factor 3. And for data in those tables, each piece of data will be copied to 3 different nodes. Okay, so that's the meaning of a replication factor of 3. If it would be replication factor of 5, then data would be copied to 5 different nodes. Okay. I'm telling you how this works, but it's important to understand that this happens automatically. Okay, you as a user, you need to set this setting, the replication factor. You need to think about it when you create your data model, when you determine the sizing of your cluster. But when you actually perform a query, when you read or write data, you don't have to worry about replicating it. The database does that automatically for you. Okay, so let's look at the cluster I previously showed you. We can see 5 nodes, nodes 1 to 5. And if we have a replication factor of 3, and we write this piece of data, say orange cube, it's going to be replicated to 3 different nodes. 3 different nodes are going to hold this data. And the same goes for other pieces of data. And I will talk maybe in just a bit how the database determines which nodes are responsible for holding the data. Okay, and this goes on. And you can understand that if this is our cluster, and say node 5 has a hardware problem and it breaks, it's not available anymore, and we try to read this green cube data, we're still going to be able to read it because it exists on node 1 and node 4. Okay, so this continues. Let's understand what happens under the hood when we perform a query to the database. Okay, how does the database know which nodes are responsible for each piece of data? So the way that this works is each one of our nodes in the cluster is responsible for a range of tokens. Okay, and what the database does under the hood is when we perform a query, it takes the columns that are defined as the partition key. Okay, in this table, the partition key is defined as the pet chip ID. And let's say I'm trying to write this row, the first one, with a heart rate of 120. So what the database would do is it would perform a consistent hash function, also called the partitioner, on the pet chip ID, on this piece of data, that is the partition key value. And according to the value of the hash function, it would know which nodes are responsible for this token range. Okay, now this is very important to understand. So maybe I'll repeat this. The partition key determines how data is replicated across the cluster. Now, again, this is done automatically, but as the user, you're going to be the one that's choosing the partition key column for your database. So you need to understand what happens under the hood. And there's a question by Ram, does the key space dynamically expand? And the answer is that a key space is a container for tables. So I guess you can think about it as dynamically expanding, but you can add more tables to it. Okay, so you can simply add more tables, and that way you can make it grow or expand. I hope that's what you meant. Okay, so let's talk about a few more concepts. I mentioned the key space is a container for tables. It can have multiple tables, and it determines some important settings like the replication factor. Okay, it can have one or more tables, and in an application, we can have more than one key space. Okay, so it would make sense to have only one key space if we only use one replication factor setting. However, if we have different tables that require different replication factors, then we can use multiple key spaces. So multiple tables, within these tables, we have data ordered according to the partition key. And within the partition key, we can have a clustering key and then key value pairs. And I know that's a mouthful, but I have more diagrams and I will explain this in more detail in just a bit. Great, so I talked about the replication factor. Another super important concept is the consistency level, abbreviated as CL. If you remember on the very first slide, or one of the first slides, I talked about eventual consistency. And in ScyllaDB, the consistency is tunable. And that means that we, as the users who design our application, we can set the consistency according to the requirements from the database. Okay, so consistency level is defined as the number of nodes that must acknowledge a read or a write request. Some example values are 1, quorum, or all. And this can be set per operation, right? So maybe let me give you an example to make it more clear. So if we have a cluster that has 5 nodes and the replication factor of 3, then each piece of data will be copied to 3 different nodes. If I set a query, say a read request that has the consistency level set to all, it would mean that all 3 replicas must acknowledge this read request, okay? If one of my nodes, my replica nodes, is unavailable, it's down, then my read query would fail, right? Because not all the replica nodes are available, and I define the consistency level as all. In the same exact example, if I define the consistency level as quorum, then even if one node is down, 2 out of 3 nodes are still available, and my query would be successful. Okay, so you can easily understand the trade-off here between availability and consistency. And maybe another example, maybe let's talk about the application. So if we have an application where, so it's an example that I use in some of the slides here. Say we have an IoT application. So we have some sensors and we send, like the sensors are on our pets, on a dog, and every second we read the heartbeat of our dog and we write that to the database. Okay, that's our application. So even if we miss one write for 1 second, it's not that big of a deal, right? Because we're writing every second, one write didn't succeed. It's not a big deal. Maybe we can set the consistency level to be rather low. However, in the same application, say we're now aggregating some of the data that we wrote, and we're doing some analysis, and we're trying to show the user a report of the health of their dog or whatever. In that case, maybe we would want to define the consistency for that query to be higher so that there are no mistakes when we provide this very important information to the user. Okay, so the same application, different queries can have different consistency levels. Okay, so there is a question. Does this architecture hold also as a master node or cluster manager, such as Yarn is Spark? So I'm not familiar with Yarn. However, in ScyllaDB, Apache Cassandra, and DynamoDB, so all nodes are equal, and we don't have the master slave or manager, or there are different names for this. All nodes are created equal. Okay. Let's talk about multiple data centers. So I mentioned we can have a cluster of many nodes, even hundreds, running in different locations around the world. And let's look at an example. Say we have users from around the world, and we can create a cluster which has nodes on data centers in 3 different geographical locations: the US, EU, and somewhere in Asia. Okay. ScyllaDB is built to be topology aware, so it would know that the nodes are placed on different data centers, and even it's even possible to define the database to set it so it's aware of the different racks or zones within each data center. And the reason for that is that, well, there are many reasons for us to want to use data centers and for the database to be aware of the data centers. One would be just performance reasons, right? So it makes more sense if my user is, say, here in China, to serve requests for that user from a data center in China, just because if we send the request to the US, it's about 80 milliseconds or something like that, because just the time it takes for, physical, because of physics, it takes time for data to travel from Asia to the US. So we would get a better performing application if we serve users from a data center that's closer physically to where they are. That's one reason. Another reason can be compliance. So maybe some country in, say, Asia has a government law that mandates that all the data for these users would remain within that country, or maybe within some geographical region, say the EU. So by using data centers and defining the settings according to that, we can do that quite easily. And the last one, which is maybe the most important reason, would be, again, high availability. Okay, so imagine we have 3 data centers and an entire data center goes down. Say there's, I don't know, an earthquake in the US. Very, very unlikely for a data center to go down. But still, let's imagine it happens. Many websites would fall, and services would not work, but our database would still be up and running because it would be serving requests from the Asia and the EU data center, okay? Remember, the data is replicated and we have multiple copies. And I won't go into the details, but it's possible to use something called local quorum and to update the data to the different data centers asynchronously, okay? So the user would not be impacted if we write data, say, to the EU. The user would get an acknowledgement his request was successful, but the data would be propagated to the other data centers in an asynchronous way. And there was a question by Aviv. Aviv is asking, what is the difference between quorum and the second one? Wondering what's the second one. Okay, so second one, I guess, is local quorum. And local quorum is... Right, so local quorum is specific for when working with data centers. Okay, even if you're not working with data centers, it's a good practice to set the consistency level to local quorum, which basically won't mean anything. But if in the future you decide to scale your application, say your company grew, you have more users, and you decide to use another data center, then you won't have to make configuration changes, and you'll just add another data center and use local quorum instead. Okay. But also, it's of course possible to, even if you do set it to quorum, to later change it to local quorum, but that's out of scope for this talk. There are procedures for how to do that.
I also saw the all option.
Sorry, which option?
In the previous slide, I saw quorum, local quorum, and all.
Right. Right, so all would be the highest consistency level. All would mean that, say we have a replication factor of 3, then all 3 replicas must acknowledge the query. And that can be useful if you require high consistency, but the trade-off is that if some nodes are unavailable, your application will have a lower availability. Okay, so again, we go back to that slide about the trade-offs between consistency and availability.
Thank you.
Sure. So I have quite a lot of material to cover, so let me go a bit faster. So this is an example from a customer. I think it was Kiwi.com, a travel agency company, and there was data center fire, actually. I think it was in France or Germany, and quite a lot, I think thousands of websites went down, but they were using ScyllaDB with a multi-data center topology, and they had 0 downtime. They were able to continue serving requests, and they didn't lose any money. We have a detailed blog post, I think, about it. If you're interested, let me know, or you can probably Google it and find the exact case of what happened. So let's skip the poll question. And let me talk about the read and the write path. Okay, so I talked about how data is written, how it's replicated, the replication factor, and the consistency level. Let's look at an example for what actually happens when we read or write data to an example cluster. So what do we have here? I'm going to go over an example of a write request, and we have our client. Usually this would be in real-world applications. So applications interact with the database using drivers, okay? In the example lab that I showed you, I connected directly to the database using the command line interface, but in a real-world use case, it would be done through drivers. So say we have a client here, an application, and it sends a write request to one of our nodes in the cluster. We have 5 nodes in this small cluster. V, W, X, Y, and Z are the nodes. And the definitions are replication factor of 3. Okay, and if you remember, that means that each piece of data is replicated 3 times. And for this specific query, if you remember, the consistency level is defined per query. So in this example, the consistency level for this query was defined as quorum. And what does that mean? It means that a majority of our replicas need to respond to a given query, okay? Now, I mentioned that in ScyllaDB, as well as Cassandra and so on, all the nodes are created equal, and that means that all the nodes can serve requests. So the client asked node V, and just for this specific query, node V will be designated as the coordinator node. Now, what node V does, if you remember, it performs the consistent hash function on the piece of data. This happens under the hood, but this is what happens. And according to the given tokens, it understands which of the 5 nodes are the replica nodes. In this example, it's nodes W, X, and Z. And node V sends that request further along to those 3 replica nodes, telling them to write this piece of data. We can see that they indeed write the data, and they send an acknowledgement back to the coordinator node. However, for some reason, the acknowledgement from node X to node V doesn't pass. Say there's a network failure here, and the acknowledgement doesn't pass. What do you think would happen next? What would node V do? Would this query be successful, or would it fail? If you can quickly write in the chat window, what do you think would happen in this case, in this example? Replication factor 3, we have a write, we wrote it to the 3 replicas, but one of the acknowledgements failed to pass through. Does anyone have any guess what will happen in this example? Will the query succeed or not? Anyone? So I see there are different opinions, and the correct answer is that it will succeed. Okay, so node V sends an acknowledgement back to the client, and the operation succeeds. And the reason is that the consistency level is set to quorum. But if you think about this exact same example and the consistency level, if it was defined to be all instead of quorum, then it would have failed. Okay, so it all depends on the consistency level. If it would have been defined as all, then all 3 replica nodes must acknowledge the request. Because it's defined as quorum, then only 2 out of 3, which is the majority, need to acknowledge this request. Okay, so that's just to give you an idea about the importance of making those settings and of what happens under the hood. Yeah, I can talk way more about this example, what would happen, what happens if a node is down. There are different mechanisms to make sure that the data is written to the node when it goes back up. And that's a whole other topic that is out of scope for this talk. And for read, it's similar. I'll skip it just because we're almost out of time. Okay, basic data modeling. So yeah, we have just 5 minutes. Yeah, let me just say a few words. If you're coming from a relational background, in NoSQL data modeling, specifically in Scylla as well, when we do the data modeling, we have to think about our application and not just about the data. Actually, this figure is not that great. I have to fix it. The data should be here next to the application. So instead of the application being considered last, as we do in relational data modeling, when we data model for NoSQL database, we tend to think about the application at the very beginning, together with the data. So we have to think about which queries we're going to perform, how often we're going to perform them, and what would be the performance impact. Things that we take for granted in relational databases, which ensure ACID transactions, basically, or denormalization or stuff like that, is more complex. It's possible to do a NoSQL database, but we have to put more thought into the data model and take into account the application at the very beginning. So there's an entire course on data modeling in ScyllaDB University. Yeah, I recommend you check that out because we're almost out of time, and I won't have much more time to talk about that. Before we finish, I want to show you the high availability lab. I'm not going to have enough time to run it, but I just want to show you how to get started with it. So I'm going to share the link with you again afterwards. And again, this is a platform which allows you to run basically a virtual machine and a command line within your browser, so no prerequisites. By the way, the links that I will share with you will probably be a different platform, not Killer Coda, but it's the same. You have the exact same lab. So I'm going to start a 3-node cluster this time. So I'm using Docker. The command is very simple. I give it the node name and the Scylla version. And for the other 2 nodes, in addition to the Docker command, I also give it the IP of the first node, right? Because it needs to find the other nodes in order to connect and create a 3-node cluster. And I see in the chat window there was a question: is the coordinator assigned or elected? So that's a good question. Yeah, it's complicated to answer in just one word, but maybe I'll try to explain. So any one of the nodes can be a coordinator node, and the client or the user or the application determines which node is going to be the coordinator node. And any one of the nodes can be the coordinator node. However, if you're using a smart driver like the ScyllaDB driver, then the driver will choose a node that is already a replica node. Okay, so it's called token-aware drivers, and that will save us the extra hop from the coordinator node to the replica nodes. Okay, so that will just improve performance, but that's just an optimization. If you're running an example and you don't really care about performance, you can choose any one of the nodes. And by the way, Scylla drivers are not only token-aware, they're also shard-aware. So they will choose the specific shard within the node that has the data, and that again goes together with high performance. Okay, so I just sidetracked, but we have our 3-node cluster. Let's see if it's up and running. I use the node tool status command, and hopefully it's up and running, but it's not. I can see only 2 nodes are available. So yeah, this typically takes, I don't know, a minute or 2 for the nodes to find each other, to sync, and to be available. Let's try again. And yeah, until it starts, I'll continue. So I connect to one of the nodes, and here I choose node X. So it's going to be the coordinator node. I connect to it with a CQL shell, just like we saw before. I create a key space with a replication factor of 3. Oh, actually, this might fail because I was impatient and I didn't wait for my cluster to be up. So I would create a key space, a table, and insert some rows. And without actually showing you what happens, you'll have a chance to run this on your own. What you're going to learn in this lab is you're going to actually see an example of what happens when we read and write data to a cluster while simulating a situation that some nodes are unavailable. Okay, so because we're using Docker, it's easy to simulate that. We just take down the Docker instance, and then that would create a situation or a simulation of a situation where a node in our cluster is unavailable. Okay, so in this lab, we're going to be reading and writing data while simulating a situation where some of our nodes are unavailable, and we're going to be playing around with the consistency levels. Okay, so you're going to actually learn by playing around with it and seeing what happens. Okay, so we're pretty much out of time. Again, I will share the link to this lab with you. And there is a question. First of all, thank you for the feedback. will it include data quality control in a further session? So I'm not really sure what you mean about data quality control, but let me go back to my slides. And yeah, I want to share one useful resource with you. So I talked about Scylla University, where you can learn more topics that I didn't cover and go more in depth. Another very useful resource is our community forum. So at the very beginning, I said ScyllaDB is open source. It's backed by a community. And we have a community forum where community members help each other. They share their use cases. And also our engineers and developers hang out there. So if you have a question and we didn't have time to answer it today, or if you think of a question later on, as you're taking the labs or the courses, yeah, just check out the forum and ask your questions there. And you're going to get answers, hopefully. Yeah, at least I'm there and I'll try to help. I'll share my email with you. Is it written here? Yes. So guy@ScyllaDB.com, write me directly. You can see my Git profile and LinkedIn. If you have any feedback about this, if you'd like to see another talk on a different topic, feel free to shoot me an email, or you can find me on the community forum. Yeah, and that's it. Thank you for joining, and you can expect the email with the links and the slides probably tomorrow. So that's it for me. Thank you very much. I hope you learned something today.
Okay, thank you.
Sure.
Yeah, thanks, Guy. Appreciate it.
Thank you.
Yeah, thank you, everyone.